All right, let's continue with some other examples of proving identities. Prove the following identity. Sine of theta over 1 plus cosine theta equals 1 minus cosine theta over sine theta. So one of the tips is to choose the more complicated side, but these look pretty equally complicated, so it doesn't really matter which one I'm going to start with. So I'm going to start just by rewriting the side I'm choosing, which is the left side, sine of theta over 1 plus cosine theta. Now, if I'm trying to get to this other side, right, I'm kind of putting it in my little lockbox here. I'm not allowed to do anything, but I am allowed to look at it. And so I see that, I have 1 minus cosine theta and sine theta on the bottom. So I'm not really quite sure how I'm going to get there. One thing I did notice before, right, is that this difference of squares idea. So that if I have a squared minus b squared, this is the same as a plus b times a minus b. So if I want to think of it that way, well, what if I thought of 1 plus cosine theta as kind of this a plus b here, and I multiplied it by a minus b? So is that allowed? Well, it's only allowed if I'm thinking of it as multiplying it by 1. So I'm going to say this is the same as if I have sine of theta over 1 plus cosine theta, and I multiply this thing by 1 in the form of 1 minus cosine theta over 1 minus cosine theta. So this fraction here is equal to 1. It says I'm just a little 1 hanging out, but of course it's kind of this fancy 1 that I've chosen. So how's that going to leave the numerator? So the numerators multiply, so I get sine of theta times the quantity 1 minus cosine theta in the numerator. And then the denominator is 1 plus cosine theta multiplied by the quantity 1 minus cosine theta. Okay, this seems to be getting worse instead of better, but that's kind of how these go some of the time. Now, what I know is now I have this right-hand side of the difference of squares. And why is that helpful? Well, because I wanted to kind of look at like the left-hand side of the difference of squares. And so I don't even need to know that formula in order to know that happens, because if I just FOIL this out, so 1 times 1, the denominator here, so 1 times 1 is 1, 1 times cosine theta, and then 1 times negative cosine theta, I can see that those are going to cancel out. And then when cosine theta and minus cosine theta multiply together, I get 1 minus cosine squared theta for the denominator. The numerator is still just sine of theta times 1 minus cosine theta. Now I'm kind of peeking at what do I want this to turn out to be. I want it to turn out to be the right side. Well, the right side has 1 minus cosine theta in the numerator, so I want to leave that alone and not multiply the sine theta in. I don't want to do that because I know I want that 1 minus cosine theta to show up. Okay, so what is the point of all this? Well, 1 minus cosine squared theta, we say, that's just equal to sine squared theta because of that Pythagorean identity, right? So it's just asking you to kind of remember, put all this stuff together. And again, it gets easier as we do a bunch of these, right? That's the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. But subtracting cosine squared theta from each side, that is going to give me 1 minus cosine squared theta is equal to sine squared theta, which is what I want here. Okay, numerator is still sine of theta times 1 minus cosine of theta. And if that's happening, then now I can see that there's a sine theta factor in both the numerator and denominator. And so if I cross out a sine theta in the numerator, that leaves me just 1 in the denominator. So I'm just going to rewrite that equals 1 minus cosine of theta in the numerator over sine of theta in the denominator. And that is, I've reached the other side, so I'm good to go. All right, let's look at C. Sine squared theta minus tan theta over cosine squared theta minus cotangent of theta equals tan squared theta. Well, it'd be hard to argue that the left side is not the more complicated side, right? It certainly is. So we are going to start here. And so to start, you always want to write down the original expression before you do anything else. So I'm going to start with the side that I'm picking. Because you really want to create this mathematical path from the left side to the right side. In this case, that's the direction we're going. So we're locking up the right side here. And we want to show that we're going to go there. And so to start that path, you need to write down that left side, kind of in your own handwriting, right? So we're starting this path. Okay, so how are we going to get to just tan squared theta? Well, the thing that I think I come back to the most, or the technique that I rely on the most, is writing everything in terms of sine and cosine and seeing if that kind of gets me anywhere. So let's try that. This is going to be, let's see, sine squared theta minus, okay, tan theta. That's sine of theta over cosine theta. Okay, all over cosine squared theta. Okay, that's already a cosine. And cotan is going to be cosine of theta all over sine of theta. Okay, so what could possibly help us here? Well, here I want to look at, I have this kind of fraction within a fraction, and I want to focus on its denominators. So I have two of those, right? I have sine theta over cosine theta in the numerator and cosine theta over sine theta in the denominator. So when I have that, I want to get rid of those. And I can only get rid of those if those factors are part of my like kind of fancy one that I can build. So I'm going to build a little one to get rid of those. And the numerator and denominator are going to be constructed the same. The numerator and denominator both need to have cosine theta and sine theta as factors. So I'm going to have cosine theta times sine of theta over cosine of theta times sine of theta. Okay, so what's going to happen is this cosine theta sine theta is going to come in and multiply by the two terms in the numerator, and cosine theta over sine theta, this one is going to come down and multiply by the two terms in the denominator. So why are we doing that? Well, it's going to get worse before it gets better, but that is math for you. Okay, so the first thing that happens is I have my cosine theta sine theta times this sine squared theta. So what happens is I just start kind of collecting factors. I get sine cubed theta, because now there's three sines, times cosine of theta, minus, okay, so now I get sine over cosine times cosine times sine. Well, the good thing that happens is since cosine is in the denominator, it's going to cancel with this cosine. It just leaves me with sine squared theta. Okay, all over. So where are we at here? This fraction bar that is in that expression above is just this fraction bar here. Okay, so now I've got two more terms to go. So cosine theta times sine theta times the cosine squared theta. Nothing cancels out. So I get, I get cosine cubed theta times sine theta minus, something good is going to happen here because I have sine theta in the denominator and sine theta is part of the factor that's coming in. So those are going to cancel in this one. And then it's just going to leave me cosine theta times cosine theta. Okay, has this gotten better yet? All right, not quite. Let's try now applying factoring because I'm seeing some common things and that could help us. So the numerator, the greatest common factor is sine squared theta. So if I pull that out, what's left in each term, the first term leaves sine theta cosine theta minus 1 all over, well, in the denominator, the greatest common factor is cosine squared theta. Let's see what that leaves behind in each term. The first term, it leaves sine theta cosine theta. And again, I'm writing the factors in that order to show what's happening here. The second term is cosine squared theta, and so when that gets removed, it just leaves a 1. And so what I see is that they're just leaving the same factor behind, which is very helpful. So let's see, these cross out, and that just gives me sine squared theta over cosine squared theta. But this is just tan squared theta, which I was after all along.